Okay, so now let's get back to how does allostery work? Two models. We have the concerted model. All right. I like to look at the concerted molecule as a all or none type of model here. Within this conversation that we're going to have now, we have to understand what these circles and squares represent. Okay? And we are going to focus on hemoglobin, just because that's the protein that we've been talking about so long. So we see here we have 4 circles representing the hemoglobin, the subunits. Now, those subunits, let's say the circles, okay, are going to be low affinity, which then would mean that is what? The T state. And then we will say the squares, okay, is going to be high affinity, and that's going to equal the R state. Okay. Now that I'm thinking about this a little bit more, let's not say we're talking about hemoglobin here, because I don't think that's a good example. Okay? And the reason why I think using hemoglobin here as a bad example is because I implied that when we look at the T and R state, it's between the alpha and the beta switching, it's rotating, okay? But this slide right here kind of implies that the alpha state kind of changes conformation from a circle to a square. And there might be some truth to that, a little bit of this, but it's mostly that. But this method right here or this model here is talking about the conformation of each subunit. Okay? So let's just talk about this model and not necessarily relate it back to hemoglobin, even though it might work a little bit. Okay? So there's this idea here that we have low affinity states and high affinity states for whatever ligand that we're looking at. So we'll get rid of that T and R. So what happens here is that when a ligand binds, okay, when that ligand binds, it then turns into, you see how all of them change? You see how one ligand binds, there's 4 circles, and then it turns into what? All high affinity states. And then that high affinity state can grab another ligand. Okay, and then why do we have equilibrium arrows? We have to, because if we go back to hemoglobin, what does it do? Binds oxygen, releases oxygen. Okay? It has to be an equilibrium process. But how that equilibrium process looks is this model says, hey, we could have a situation where when that ligand binds, that first ligand binds, it changes the conformation of the other 3 to high affinity. Okay? So it's like all or none. Meaning once that ligand binds, all the pieces change. And so you could see in a second model, they're going to say, no, it doesn't work like that. It's going to be more sequential. And the sequential method or model is a whole lot more complicated. It's a way more complicated looking. But what I want you to focus your attention on is the blue part right here. That's kind of the most important thing to zoom in on. But when you take a look at that, when you have a ligand that binds, that one ligand, what does it turn into? Well, just that one ligand, that one subunit changed from a low affinity to a high affinity, but all the others remained low affinity. Do you see can we contrast that between the concerted and the sequential? One ligand binds, and it turns into all high affinity. Whereas in the sequential, when one ligand binds, only one of the subunits And then it just has all these different equilibrium paths. Okay? It can get very, very complicated. But if you just go down this one, you kind of can see what's happening here. When the second ligand binds, that second subunit changes into a high affinity state, and then the other two remain circles. Okay? It is complicated. Okay? And if you don't understand it after this 3-minute discussion, 5-minute discussion about it, that's okay. Because it is just a lot going on. And so there's these different models that help us explain how does allostery work. And we haven't nailed it down to this is how it happens. There's different theories out there. So the main point then, the takeaway is, we know allostery works because we can see it in the data. That process of how it does that, we have some ideas. Okay, so just make sure you know the difference between these two models. Heavens no, don't you dare start memorizing every single step on that graph, okay? That's not the point. It's just, what's the difference between a sequential and the concerted, okay? If you can put that into your own words, then I think that's really, really good. And you'll be just fine. So if we come back to this little graphic right here, you'll see this in your textbook. And I just want to go over this so you guys have a good understanding of what's happening. With allostery or allosteric proteins, what I want you to see is that there's that protein or that subunit and this subunit. And we see based off of the color code that blue is the most stable part of the protein, green not so much, and then the pink/red just really, really bad. Really high in energy and unstable. And so what happens here, we have these proteins in a low affinity state. And then what happens? We have just one ligand bind. Okay? What does that one ligand do? Well, it stabilizes that subunit right there. Do you see how we went from red and pink to green right there? It's not blue, but it's more stable than it was because it went from pink to green. And so that's a stabilizing effect right there. But when that one ligand bound over here, I want you to focus your attention on the difference here. Yes, it's still green and pink, but you see how the orientation of this guy right here versus the orientation of that guy. What's happening to that? After that first ligand binds, the top, I don't know if I can. Look at the position. The ligand here binds and now the position changes. What's happening? It's positioning to turn into that green piece right there. And what does that green piece do? It kind of holds in that second ligand. And so allostery is just looking at what effect does this ligand have on the other subunit. And you can see it is starting to position, it's changing its conformation to make this piece right here a higher affinity. A higher affinity for the ligand. And how do you get more affinity? You change the conformation in such a way that says, hey, ligand, come inside. It's a great place to stay. But you can see at this stage of the game right here, the ligand's like, nah, I'm not going to waste my time. It doesn't look like I can even go there. It doesn't feel like a good place to be. So this is a cartoon that just helps us explain allostery and how one ligand affects the other. Now, we could draw a completely different cartoon if we wanted to. And let's say if we have a heterotropic regulator. What if I stuck one right here? Okay, if I stick a heterotropic modulator, what do we think could happen? Well, when that green ball binds, then that's going to make that ligand release. Something like that. So a protein, an enzyme, protein, they can have multiple sites for multiple modulators. So hemoglobin, the binding site, is in the heme. Okay? But where does CO2 bind? Okay? And we'll learn more about that, but it doesn't bind in the same spot. So carbon dioxide and oxygen do not bind at the same spot. So you have a protein that can have many modulators, and it depends on what molecule binds and where it binds. And those sites of modulation is oftentimes a big drug target. That's what drug companies are trying to figure out. Can we build a molecule or a small peptide that will target that binding site with high specificity, or what? A very small KD. And if they can design something like that, then they have a potentially good drug molecule that they've made. Okay. Do you guys have any questions or comments? Just smiles? Just smiles. Okay, let me just double check one more thing. Hi. So that explains that. Okay, so next time we're going to talk about the carbon dioxide and the VPG and how that affects hemoglobin. And so we're going to use a lot of those math terms. KD, high affinity, low affinity, T state, R state. So I highly encourage you guys to watch those videos, do a little reading if you need to make sure you know those terms. So when we come to class on Tuesday, we can just jump into some things and you'll know what's going on. Okay, so we'll call it a short day. You guys have a good rest of your week.